Welcome to EDU World Space.
Because the pressure varies with depth, the force on the wall will also. So in force, we're going to have to integrate. First, we're going to say that for part A, the gauge pressure P is equaling the density times G times Y. We know that the differential of the force will be equal to the pressure times the differential of the cross-sectional area. And so this would be equaling the gauge pressure, rho gy, multiplied by B times dy, the differential of the depth. And so the force would be equaling the differential of the force. This is equaling the integral from 0 to h, the total height of the gauge pressure, multiplied by B dy. And we can then say that the force is equal to 1/2 times the density rho times the acceleration due to gravity times b h squared. So this would be our answer for part A. And then we can say that for part B, the lever arm for the force dF about the bottom of the dam is h minus y. So we can say lever arm for force dF equals h minus y. And so the torque caused by that force, we can say the differential of the torque would be equaling h minus I times the differential of the force. And we can then say that the torque is going to be equaling this integral of course, d tau. This would be equaling the integral from 0 to h of h minus y multiplied by the gauge pressure, rho gy, multiplied by b times dy. And so we can say that this is going the torque tau is going to be equaling the rho, the density, times g times b times the integral from 0 to h of hy minus y squared multiplied by dy. And so we can say that we can continue and say this is going to equal rho gb. This would be multiplied by 1/2 times hy squared minus y cubed over 3 evaluated at 0 and at h. And so tau, the torque, would be equaling 1/6 times rho g b h cubed. Consider here as caused by the applied at a distance from the bottom d. So we can say that the torque is going to equal this, but this is going to equal the force times d. And so this would be equaling 1/2 times rho g b h squared times d. And so we can say that d is going to be equaling h over 3. This would be our answer, finally, to part B. Now, to part C, we have to prevent overturning. So in order to prevent overturning, the gravity about the lower right front corner in the diagram must be at least as large or as great in magnitude as the torque caused by the water itself. We know that the lever arm for gravity is half of the thickness of the dam. So lever arm for gravity, we can say equals half the thickness of dam. And so we can say mg multiplied by t over 2 has to be greater than or equal to 1/6 times rho g bh cubed. And so the density of the concrete multiplied by hbt multiplied by g times t over 2. This is going to be, again, a greater than or equal to, we can put it down here, 1/6 times the density of water times g b h cubed. So now we can say that T over H is greater than or equal to the square root of the density of water divided by 3 times the density of concrete. And so this would be equal to the square root, the density of water, 1,000 kilograms per cubic meter, divided by 3 times the density of concrete, 2,300 kilograms per cubic meter. And this is equaling 0.38. So in order to prevent overturning, T must be greater than or equal to 0.388. This would be our final answer. That is the end of it. Thank you for